This is a short tutorial on Python generators. Generators lazily generate values, which means they only create them as needed, leading to lower RAM usage. If you're working with large datasets, generators can be very useful to process that data chunk by chunk instead of trying to keep it all in memory. They're defined just like regular functions using the def keyword. The main syntax difference in the generator itself is that you produce values using the yield keyword instead of return. Let's see an example to make this clear. A classic example of when to use a generator is the Fibonacci sequence. What is the Fibonacci sequence? It's a series of numbers where each number in the sequence is the sum of the two previous. It begins with 0 and 1, so the next number is the sum of 0 and 1, that's 1. The next number is the sum of 1 and 1, that's 2, and so on. It's an infinite series of numbers, so it's obviously not going to fit into memory. This is a great situation for a generator. Let's implement that first. So let's first define a function called Fibonacci, and we'll have two values a and b that we'll set to be 0 and 1 initially, like the beginning of the sequence I just showed. Then, since this is an infinite sequence, we're going to have an infinite loop while true. Then we'll yield the first value, a, and then we'll set the values to be ready for the next loop iteration. So we'll redefine a to be b, and then we'll have the next value be a plus b. So that should do what we want. At this point, we are ready to use our generator. So how do we do that? It's a bit different from a regular function because when we call this generator function, it actually returns a generator object. So let's import gem. And then let's have our generator be called g. And we're actually going to call this function. So what is g? It's a generator object, Fibonacci. Now generators are iterators, and they're going to produce their value after the yield keyword. Since they're iterators, we need to use the next built-in function on the generator object to advance its execution to the next yield keyword. So if we want to advance its execution again, we again called next g. And we can just do this indefinitely, and it's going to reproduce the numbers that we saw in the slide previously. That is the basic usage of a generator that produces infinite values. So now let's think about another example that shows us what happens when we run out of values to yield. And this is based on an example that I ran into at work. A colleague had two pieces of code. This is going to be highly simplified for edification purposes here, but basically two pieces of code that were separate. He had one piece of code that is going to be in this run all update task function that contains a bunch of logic about various update tasks that he wanted to perform in a loop. And then he had a totally separate piece of code that was going to share progress information about the updates with the user. It's actually in a GUI. And the question was, preserving this structure, what's a good way to get the progress information out of run all update tasks to the update function such that the user can get updated while these update tasks are occurring? And if we don't do that, then we're going to not report the progress until the entire thing is done. And so this is a situation that could be handled nicely using a generator. Let's see how. Okay, so here's the skeleton version of the scenario I just described. We have our function run all update tasks that has the logic of what tasks need to be performed, and that returns progress information as a string to the caller, which is going to be this update function that's going to actually print out the progress to the user. So preserving this structure, how can we use a generator? So first, a thing we can make run all update tasks a generator function. So to do that, we will want to yield incremental progress. So we'll add a yield here, and we'll say number task of however many there are is complete. And so that'll be this index, and then the number of tasks that there are. And then we'll get rid of our return statement since we don't need it in our generator. So that should be good. So let's try and use it interactively. Let's import prog, and then let's call the function to get the generator object. So now we can call next on G, which is our generator object. We should take about a second and then return the progress. Seems to be doing what we want. And then once we run out of values, the generator is exhausted. And the next time we call next on an exhausted generator, it's going to raise this stop iteration, which is actually how an iterator indicates that it's exhausted. So let's now use that generator. Since we just said that it's an iterator, so we can use a for loop which will handle stop iteration for us to exit the loop. So instead of calling this function to get the progress result, we're going to call this function and get the generator. And then actually let's call this something better. In this case, updates. So for task progress in updates, what do we want to do? We want to print the task progress. So that should do what we want. Let's just run the whole thing on the command line. So we should see each task complete. Great. So that's how we can use a generator in this scenario. Let's recap what we now know about generators. Generator functions are defined like regular functions using the def keyword. Inside the generator function, we produce values using the yield keyword. In order to advance the generator to the next yield keyword, we call next on the generator object, which is returned from the generator function. Finally, when a generator is exhausted, it raises stop iteration, which we can handle gracefully in our code. That's a little primer on Python generators. I hope this was useful and thank you for watching.